So as we get into chapter 2, part 2 here with scientific notation and sig figs, we want to take note of a couple of things. So first of all, scientific notation. Scientific notation has two parts, basically. The first part of scientific notation is the decimal part. Now, the decimal part of the scientific notation shown here in yellow gives us an idea of how many digits are in our measurements and what the magnitude of those digits are. The exponential part here tells us how many times we have to move the decimal to get to the number that's actually being represented. So scientific notation is a shorthand. It's a way of taking really long number strings and making them really more condensed. So again, we've got the magnitude, which is the decimal part. What is it? What is the measurement itself? And then we have the exponent, which tells us how many times we need to move that decimal to the left or to the right. And so the exponent here, which is we abbreviate by n, gives us this way of moving left or right for that number. So if I'm looking at that exponent, what I need to look at, what I need to determine is, what am I doing with this decimal number? And so if n is positive, that indicates that we are dealing with a large number. And so that n tells us how many times do we need to move that decimal to the right to give us the bigger number that we are actually seeking. If n is negative, we're dealing with a small number. N tells us how many times to the left we need to move that decimal to show how small that number actually is. Now, this is kind of written as opposite of what's on the screen here, because the screen here is talking about how to turn a number into scientific notation. So let's say that we were looking at a number like this. If I'm going to turn this number into scientific notation, first thing I have to do is I have to turn it into a decimal. The decimal is always going to be number, period, and then however many numbers fit into the measurement itself. So my decimal here, what I'm going to do is I need to move this decimal not to there, but rather to here. So my decimal here is 9.41. I always have one number in front of the decimal point and a series of numbers after the decimal point. How many after the decimal point? We'll get to that when we talk about significant figures. Scientific notation always reflects significant figures. So my decimal in this particular case is 9.41. What is my exponential portion? Well, I know it's 9.41 times 10 to the something. The question is, how do I get to 9.41 from here? Well, I have to move this decimal place 1, 2, 3, 4 times. And those decimal movements were to the right, which means I'm going to have a negative exponent. So that's -4. Negative because I had to move it to the right. 4 because I had to move it 4 places over. Now, if I have a number that's already in scientific notation, So let's say I had 9.79 times 10 to the sixth. I would be reversing the process here. Positive numbers mean I'm gonna have to move it to the right. Negative numbers mean I'd have to move it to the left. I need to take my decimal 9.79 and move it to the right 6 times. 1, 2, 3, 4, 5, 6. Now, what do I do with all these extra bumps? Well, those are where I would need to put zeros. 0, 0, 0, 0. 9.79 times 10 to the 6th is the same as 9.79 million, 9,790,000. So, couple ways to keep this straight in your head. Positive numbers, big numbers. Negative numbers, small numbers. So if I'm looking at a small number, a number less than 1, I know that's going to have a negative exponent. If I'm looking at a number greater than 10, I know it's going to have a positive exponent. How do I convert between one or the other? Well, it's a matter of what way am I moving the decimal to do so. So when I'm dealing with large numbers, so the exponent here tells me how many times I'm multiplying by 10. That's where the scientific notation part comes in. Positive means I'm multiplying by 10. Negative basically means I'm dividing by 10. But again, we can think of it more as moving that decimal to the left or to the right. Move it to the left to make the number smaller. Move it to the right to make the number bigger. So just looking at this from a standpoint of, how do I do this? How do I make sense of this? Well, let's look at a couple of examples. So here's a number, 3,245. Now, for numbers like this that don't have a decimal, we can assume that the decimal point is right here at the end of the number. To turn it into scientific notation, I need to move this decimal point from here to there to get it to 3.245. I had to move the decimal point 1, 2, 3 places to the left. And so my exponent there is positive 3. And if I was confused about whether it's positive or negative, just look at the number again itself. The number here is greater than 10, so it's going to be a positive number. For the second example here, I've got a number less than 1, so I should automatically think to myself, okay, I'm dealing with a negative exponent here. The number is less than 1. It's smaller than 1. Same thing though. I gotta move that decimal point here, 3.245. How many times do I have to move it? 1, 2, 3, 4, 5, 6. 6 places to the right. So the 6 in my exponents for the number of times I had to move it. It's negative because I had to move it to the right. You can also think of it as negative because the number I'm trying to represent is less than 1. Third example, I've got 3.245 billion here. So decimal point is here at the end. I need to move it to where this first comma is. So I know it's going to be a positive exponent because we're dealing with a large number here. How big is that positive number? Well, I need to count 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's how I come up with 9 as the exponent there. And so similar kinds of things for these last two. I can see that I moved the decimal 3 places to the right here. This number is smaller than 1, so it's negative. Here I would have had to move the decimal place 1 spot over, turn 88 into 8.8 times 10 to the first. Now, what about this question? Thus far I've phrased everything in terms of, is it greater than 10 or is it less than 1? What if it's between 10 and 1? What's the scientific notation look like then? Well, in that case, I've got a decimal that is already in the proper format. I don't need to move that decimal either direction to get the proper decimal format. So since I didn't have to move it at all, I moved it 0 times, the exponent in my scientific notation would be, in fact, 0. Now, in those kinds of circumstances, how often do we see scientific notation used in these instances? The answer is we don't. In fact, we probably wouldn't use scientific notation in this next last example either, unless we were just doing it for the sake of practice. But where we see scientific notation used the most often are in these ranges here. I've got a big number that I'm trying to represent, or I've got a small number that I'm trying to represent, and I want to represent them in a concise kind of way where I don't have to write in every single one of those zeros. And if we get into the discussions that we were talking about on Wednesday, where we start looking at things on the tera scale or on the pico scale, where we're talking about 10 to the positive 12, 10 to the negative 12, you really tiresome to write in all of those zeros. If I'm representing 1 times 10 to the negative 12, it's 11 zeros before that 1. That'd be really tiresome to write out time after time after time. Let's talk a little bit about how to use scientific notation. If you have a calculator, I'd suggest that you get it out. If you don't have a calculator, you're going to need one at some point here. I'd start bringing it with me to class because there are going to be many instances where we are going to use calculators. But as far as calculators go, calculators kind of fall into 2 categories. There are the exponential model ones. So I'm using a Casio here. But if you're using a TI calculator, there is a similar function on those. And then there is the scientific notation button that looks a lot like this. When you're using a calculator, though, scientific notation is a lot easier to use than trying to type in times 10 to the exponent each time. Because one problem that you run into, I'm going to show you here on the document camera, and if you're watching this later on YouTube, you're not going to be able to see this, and so I apologize in advance because we can't get a 2-camera setup going here. But here's my calculator. So I'm using a Casio, but like I said, the functions on a TI calculator are very, very similar. Now on mine, there's a button here for exponentials, for exponents. This is my scientific notation button. On TI calculators, you might see this as times 10 to the X button. You might also see this as a secondary function. If you have in your secondary functions a one that is marked as EE, that is your scientific notation button. But here's why it's important. Especially when we are dividing by numbers, order of operations can really kind of stick up. Where you might want to put in, 36 divided by 3 times 10 to the negative fifth. And the correct answer to that is 1.2 million. But if you don't use parentheses properly and you try to put it in manually, you can end up getting something like this. 36 divided by 3 times 10 to the negative fifth. (1.2 times 10 to the negative 4). Remember, the correct answer was 1.2 million. This answer is far away from that, 10 orders of magnitude incorrect. Why is that? Well, because your calculators follow the order of operations. And so what I just told my calculator to do is I told my calculator to take 36, divide by 3, and then multiply by 10 to the negative fifth. I told it to do those things in that order. And so it said, sure, 36 divided by 3, that's 12, multiplied by 10 to the negative fifth is 1.2 times 10 to the negative 4. Great, thank you. But that wasn't the correct answer. The reason it wasn't the correct answer is because I didn't use my scientific notation properly. So when you're doing scientific notation, you have to use your exponential button. That is going to be the way that is going to get you to where you're supposed to be when you're supposed to be there. So how do I do that? When I'm putting in my number, I can do one of two things. I can either use parenthesis buttons, or I can use that exponential feature right there. So exponent turns it into a value here. This is standing in for scientific notation on the Casio. Now I put in -5. And now I hit enter, and it gives me the correct answer. Now, if you're using a TI, and there are a lot of different models of TI, but they all kind of follow the same pattern, what you're looking for here is, it's usually on the comma button. It's the secondary function of that comma. And so you're going to do the same operation. 36 divided by 3 times 10 to the negative fifth. And so on those calculators, it's going to show up as lowercase e. That's scientific notation on that Casio. And if you do that, again, it's going to come up with the correct answer there for you. So learn to use for functions properly. They're going to save you a lot of time. They're going to save you a lot of headache. And if you're not sure of how to do it, I'll be more than happy to show you how to do it for your individual calculators once we get to a spot where we can kind of work on those things. So certainly ask about that during office hours or anything like that. Reach out to me individually or just stop by, on your way out, and I'll show you how yours works if you're not sure. Now, as far as scientific notation goes, generally speaking, there are 3 functions that you're going to do with scientific notation: multiplication, division, and raising to a power. And I just showed you on the calculator how you can do each of those things. Let's take a moment here, though, and let's try to do a little bit of practice together with converting things to scientific notation. So our first example here, we've got something north of 9 trillion here. Scientific notation for that, I can see the decimal point is here. I need to move it to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm gonna get a big decimal here because all of these digits have to come along for the ride. 9.0000000655500 times 10 to the 9th. Now, why did I have to include all of those? That's part of our significant figures discussion. But one of the rules for significant figures is that if there is a decimal point, all of the digits leading up to and following that decimal point are significant, so long as there's a non-zero number that starts the whole thing. And since we're starting with a 9 there, that means that every single digit in that measurement was significant. On the other hand, a number like this, none of these zeros are actually significant because there's no non-zero number to start it. So I really only need to concern myself with the 8.34. I move the decimal 1, 2, 3, 4, 5, 6 spots to the right. And so that means my exponent is -6. For 1.21, I can leave it just as 1.21. It's between 1 and 10. If I want to turn it into scientific notation, I could. The exponent there would be 0 because I haven't moved the decimal place at all. For 14.82, chances are pretty good we could probably leave it alone as it is. If we had to turn it into scientific notation, we would want to move that decimal point 1 over to the left, 1.482 times 10 to the first, and it would be +1 because we're dealing with a number greater than 10, so we have to move it over to the left. For these last two, again, without a decimal place here to signify where the number ends, we can just assume it ends here at the end here. I need to move it 1, 2, 3, 4, 5, 6, 7, 8 spots. So 2.998 times 10 to the 8th would be the correct number. Why didn't I include all of those zeros here? Well, unlike the first one, there's no decimal point in the number here to tell me that all those zeros are actually significant. We'll talk about this in a second, but in these kinds of circumstances, a lot of times zeros are there merely to show us how big or how small the number is. So telling us the difference between 2,998 and in this case 299,800,000. The last one we could probably leave as 63, or if we had to turn it into scientific notation, be very similar to the one just above it. We move that decimal 1 spot to the left, so it's 10 to the first. All right, any questions with scientific notation before we talk about sig figs? Okay, so significant figures. Probably the question I get asked the most by beginning chemistry students is why on earth do I even need to care about significant figures? It seems like there's a lot of rules, and sometimes the rules don't always seem to make sense to us. Why do I need to go through all this process of knowing how many sig figs are there and how to calculate with them? And the main reason that we care is because everything that we do in the sciences starts with measurement. And measurements have limitations. If I'm trying to measure the distance between here and the water tower, there are going to be limitations to my ability to measure that accurately. And there are lots of different ways I could measure it. It's not that far from here. I could count the number of steps it takes to go from here to there. That would be one mode of measure. I could take a tape measure and stretch it out from here to there. I could use a number of different ways of doing it, but they would all have some inherent limitation to them. Some limit to the number of digits that we could report as being part of the measurement. And when we start to look at measurements from more than just measure from here to there, measure this volume, measure this distance, measure this temperature, when we start applying them to other principles, we start to realize we want to make sure that we're not overestimating or underestimating our measurements. Rounding becomes an issue. How much should I round? To what degree am I rounding? If I have this measurement and this measurement that are going into the factoring of this calculation, how much error, how much rounding am I comfortable with? This is where significant figures come in. Significant figures give us some guidelines for how many digits are actually significant and how do we apply those roundings, those measurements, to when we start to combine measurements together, whether it's through adding and subtracting, or multiplying and dividing, or any other function that you can think of. So let's start with some just general rules. First of all, we have to recognize that any scientific number that we report is going to have one uncertain digit, one estimated digit. That estimated digit is always the last digit in the measurement. Now, depending upon what instrument we use, we could end up having different layers of precision, but each of those layers of precision will only ever have just one estimated digit. Otherwise, we start to call into question the validity of the measurement itself. If I measure something and I go, okay, well, yeah, it's measured out to 8 decimal places, but I'm really only sure about the first 4. Well, the question would be, well, why did you report the other 4? They couldn't have given us that much information if we're not so certain about their accuracy. So there has to be a limitation. That limitation is one estimated digit, and only one estimated digit. So when you measure in the lab, you're looking at your graduated cylinder. You can measure, but you always need to make sure that you have that one estimated digit there. And just the one, not more than that. So let's look at some other guidelines. When it comes to significant figures, any digit that is not a 0, we can automatically assume is a significant digit. Otherwise, we wouldn't report it. If we have zeros that fall between non-zero numbers, they are significant as well. So in both of the cases here, 405 and 40.5, that 0 is a significant digit. That, unfortunately, is where things start to get difficult. What do I do with zeros that are not in the middle of a number? Well, let's look at zeros that end a number. If a 0 is at the end of a number and also toward the right of a decimal point, it's significant. So if I see a decimal point That decimal point tells me that the zeros there are significant if they come after a non-zero digit. But if they become before a non-zero digit, they're not significant. So this zero that starts 0.151, it's not a significant digit. The zeros that precede the 4 in that second measurement, they're not significant either. They are there just to express magnitude, just to express how small these measured numbers actually are. So kind of the rule of thumb here. Zeros that start a number are never significant. Zeros that end a number are only significant if there's a decimal point there to indicate their significance. And this is where scientific notation can really help us out. Because scientific notation will always reflect the correct number of significant figures. So what this last bullet point is getting to is, what do I do with a number like this? 2,800. What do I do with a number like that? Well, if I look at it just at the surface, I would say, okay, no decimal point, those zeros aren't significant. But what if one of them was? What if both of them were? Well, if they're both significant, I can put a decimal point at the end. That would indicate that they're all significant. But what if only one of them is significant? This is where scientific notation comes in. Scientific notation would allow us to say, okay, those 3 digits are significant, but the fourth one isn't. 2.80 times 10 to the third. 3 significant figures. As opposed to 4. So if you're wondering where scientific notation can be really useful to us as kind of an overall tool, this is one of the places. Significant figures are always properly reflected in scientific notation. Because we don't put anything into scientific notation that isn't significant. Otherwise, what's the point? All right, another thing that we can look at. Exact numbers. When we have exact numbers are known to infinite numbers of significant figures. They have infinite precision. Now, what are exact numbers? We find them in three places, basically. One, exact counts. So, for example, if I were to count the number of people in this room, that would be an exact number. There would be no estimation involved in that. I would count every single one of you, and that would be a precise number. If I was counting the number of steps between here and the water tower, that would be an exact number. There would be no estimation in that measurement whatsoever. Defined quantities. So, for example, I know by definition, there are 12 objects in a dozen. I know by definition that there are 2.54 centimeters in every inch. The other thing that can go into this are things like constants. So if I have an equation that has a constant value to it, like the speed of light or Avogadro's number or something along those lines, I can assume that that number has infinite significance. It's not going to be the thing that rounds my answer up or down any further. So that's all the time we have for today. I actually didn't get quite as far as I would have liked. So got a couple of things for you to think about, to consider. So this homework assignment, this post-lecture assignment, it is due on Tuesday night. What I'm going to do for you, I'm going to record the last bit of this lecture. I'm going to post it on Blackboard, post it on YouTube, and you try to watch it on your own, kind of piece together what you can of it. Think of that as Monday's class, if you want to think of it that way. Probably not going to be more than 10 or 15 minutes long. But in the meantime, work on that assignment, answer the questions, and if you get stuck on something, feel free to reach out to me and we can talk about more of that stuff on Wednesday. Have a great weekend.